Isomers are compounds that have the same molecular formula. They are divided into structural isomers. We've seen this in chapter 1. These are constitutional isomers, compounds that have the same molecular formula, but every time you write them, you can simply write them differently. So they have different connectivity of atoms. Like, for example, C3H6O, you can write it as an aldehyde. This is a DBE of 1. You can also write it as a cyclic ether, and this is a DBE of 1. Both have the same number of carbons, hydrogens, and oxygens. These are called constitutional isomers. Stereoisomers, on the other hand, they have the same molecular formula. They have the same connectivity of atoms, and this is how they part from constitutional isomers. But they have a different orientation of molecule in space, so different rotation of molecule in space. Stereoisomers are different types. You've seen the first type, which is the geometrical isomers. Geometrical isomers are cis and trans. There is no way that you can rotate the cis and go to trans unless you go ahead and you break the bond, the sigma bond between those two carbons in here. So you have to break this bond. Once you go ahead and you break the bond, you have to twist it so that you to change the orientation of this carbon in here. And this is how you can go from cis to trans. So with cis and trans, you cannot go from one to the other by rotation. This is why we call those geometrical isomers, and they are a type on their own. They have the same connectivity of atoms as you've seen, but the orientation of the molecule is different in space. And then we have two other types of stereoisomers, enantiomers and distereoisomers. To define those two, there are a couple of terms that we need to go over first, and then we will define enantiomers and distereoisomers. The term non-superimposable. Non-superimposable means that if you have a molecule and you have put a mirror in there and get its image, it's a simple mirror where you can look at the molecule and view its image in there. So as you can see, the image is the reflection of the molecule. And then if you take the molecule and you take the mirror image and you place them on top of each other, they won't align. So if they don't align, then we say that the molecule and its mirror image, they are completely different molecules in there. And we say that they are non-superimposable, and we say that the molecule is a chiral molecule because it has a mirror image. So we say that these two are pair of enantiomers. Another term is the superimposable. We're going to have some actual organic molecules as an example of those, but I wanted to start with these examples first just to bring the idea to you. So superimposable is whenever you have a molecule, you place a mirror and you look at its reflection. Now, if the molecule and the reflection align with each other, like the pair of socks, for example, then we say that these two are the same. So if they are the same, this means that they are not mirror images. And we say that the molecule and its mirror image, they simply align with each other. These are superimposable. So we say that the molecule is achiral or not chiral molecule. So by definition, an achiral molecule is a molecule that has no mirror image because the mirror image is exactly the same as the molecule. The other term that we want to define is the symmetry. How to detect symmetry? There are two types of symmetries involved, and symmetries are involved whenever the compound is achiral. The first type is the plane of symmetry. The plane of symmetry is a simple imaginary line that you can draw, and you can cut the molecule into two halves or two equal parts. Let's have an example. The line, you can draw it anywhere you want, but it has to start and pass through the molecule, something like that. So if I have a cis-1,2-dimethyl cyclohexane, I can simply draw a plane of symmetry across these carbons in there and divide the molecule into two equal parts. This is part A, and this is part B. So if you could achieve this, then you can draw a plane of symmetry in there. Notice that part A, as if it is the mirror of part B, because that plane of symmetry that you drew, it's as if it is a mirror. So if you take B, you can fold it on top of A. So A and B are superimposable in this case. Same thing, if I have this another example in here, just to show you that we can draw a plane of symmetry anywhere we want, as long as it can cut the molecule throughout. So here you go, something like this. So I can draw a plane of symmetry that passes between those two carbons in here. Okay, this is one plane of symmetry in there. So this means that this half, I can fold it on top of this half in here, and those two are superimposable. Or I can draw a plane of symmetry between those two carbons in here. This means that this half here, I can fold it on top of this half in there. So the moment you see that you can draw a plane of symmetry, then this means that the molecule is not going to be chiral. It's an achiral molecule. We'll talk about this as we proceed. Another type of symmetry is the center of symmetry. And the center of symmetry, it's the point normally that is located in the center. And it's the point where identical components, so you should have an identical components. For this one also, I can have a center of symmetry as well for this example. So it's the point where identical components are located at an opposite sides, and they are at the same distance from the point along any axis that passes through. This is called a center of symmetry. So these two types of symmetries, whenever they are present, they are going to make the molecule an achiral molecule. So the molecule actually will not have a mirror image because the plane of symmetry by itself is considered to be a mirror that is going to cut the molecule in half. So it's as if that the mirror is within the molecule itself, cutting the molecule in half and making the halves superimposable on each other. This is why the molecule will not be chiral. It's termed an achiral molecule, so it will not have a mirror image. So how to determine chiral molecules? A molecule is supposed to be chiral if you cannot draw a plane of symmetry across the molecule. If you can draw a plane of symmetry, then the molecule will not be chiral, will be achiral, and it will not have a mirror image. Something like this: water. Water has an oxygen as a center atom and two hydrogens in there. If I put a mirror and look at the reflection of the water, then I take the water in its reflection. The idea is that if I take the molecule in its mirror image and put them on top of each other, they should not align. If they align, then this means that they are the same. This means that they are superimposable, they are the same. Another thing here is that you can already draw a plane of symmetry across the oxygen in there. So if you draw a plane of symmetry across the oxygen molecule in there, you're going to be able to cut the molecule in half. So the moment you have a plane of symmetry, this means that you cannot have a mirror image, because whatever you have as a mirror image is going to be the same as the molecule itself. So that is the first case. Water is not going to be chiral and there is no mirror image for water. Now let's have the second case where we have a central atom and the three different groups around it. So you have two groups that are the same and then two groups that are different. In this case, you take the molecule and you put it in front of a mirror and look at its reflection. Anyways, if you invert the molecule, you can pass a plane of symmetry throughout the carbon in the two groups over here. And if you can draw a plane of symmetry, immediately the molecule will not be a chiral molecule and its image will be the same as the molecule. So here, since I'm able to draw a plane of symmetry, if you take B, you do the rotation, it's going to align with A. Rotation can be in any angle. And the idea for chiral molecule is that no matter what you do to rotate B, there is no way that it's going to align with A. So if you do a rotation of B and it aligns with A, this means that the molecule is not going to be a chiral molecule. It's going to be an achiral molecule and it's going to be the same. So this is why here I say that if I have a central atom and three different groups around it, then definitely the molecule is not going to be chiral because the molecule and its image is going to align and they are going to be the same. The third case is whenever you have four different groups around the central atom. Then in this case, there is no way that you can draw a plane of symmetry here that cuts the molecule in half because all of these groups are different. Then if you take the molecule and to draw its mirror image in there, and then take A and put it on top of B like I am doing over here, no matter how you rotate B, there is no way that the bonds are going to align with A. So now I would say that A is different than B. It's different by rotation. The connectivity of atoms are still the same. So all of these atoms are still connected the same, but it's different by rotation. So we would need to give them a name. We would say that these two are pair of enantiomers. So A and B are pair of enantiomers in there. Enantiomers are mirror images. This is another word for enantiomers. They are mirror images in there. And mirror images exist whenever you cannot draw a plane of symmetry. Then this means that the molecule and its image are completely different molecules. No matter what you do to rotate B, there is no way it's going to align with A. Another term that we need to define is a chiral center. A chiral center is a center that is surrounded by four different groups. Another term for chiral center is stereo center or stereogenic center. All of those are the same meaning. It's the carbon that is surrounded by four different groups in there. And in this case, we are looking at the sp3 hybrid carbon. So when you want to determine the chiral center has to be an sp3 hybridization in there. And you draw the mirror image of that sp3 hybridization. Now notice how I'm drawing the mirror image. It's the reflection. So whatever appears on the side, you're going to see it on the other side in there. So I am not changing the orientation of the bonds. So I can easily see that this carbon O bond, this CO bond in here, that is pointing towards me. This is in front. It's going to stay in front. This CH bond is in plane. It's going to stay in plane. And this bond also in plane. It's going to stay in plane. Now this one is behind. It's going to stay behind. Remember that every tetrahedral needs to have two bonds in plane, one bond in front, and the other one is going to be behind. So far we've defined the following terms: superimposable, non-superimposable, plane of symmetry, center of symmetry, pair of enantiomers, mirror images, and chiral centers, which are stereogenic centers or stereocenters. A chiral molecule cannot exist if the molecule doesn't have a chiral center. We defined a chiral molecule is a molecule that has a mirror image. And for the molecule to be able to have a mirror image, it needs to have a chiral center. So this is a must. On the other hand, not every molecule that has a chiral center has a mirror image. Center has a mirror image. We defined a chiral center that is an sp3 hybrid center that has four different groups. And there's a difference between a chiral center and a chiral molecule. So chiral centers normally they make the molecule chiral, and if the molecule is chiral, then the molecule has a mirror image. Unless you are able to draw a plane of symmetry through the chiral center, then the molecule will be achiral. And that is a different case that we will discuss as we proceed. So any tetrahedral center, any sp3 hybrid center, whether it's a carbon, here in this case I have a nitrogen, if that center is surrounded by 4 different groups around it, then its geometry is going to be tetrahedral. Then in this case it will be a chiral center and it will exist as a mirror image. So if you draw the mirror image of it, it's going to be the reflection. Just to draw a mirror in there. The mirror is simply either a solid line that you draw, or you draw a dotted line like this. Both are resemblance of a mirror in there. In the mirror image, whatever group that is behind, you keep it behind. Whatever group that is in front, you simply keep it in front. Those that belong to the same plane, you keep them in the same plane. As we said, whatever you are viewing is the reflection of the molecule on the other side. So these groups, they need to appear on the other side, but you're not going to change their orientation. If they are in front, they're going to stay in front. So here we say that A and B, they are non-superimposable because you cannot draw a plane of symmetry across the nitrogen. So these two are two different molecules in there, and we say that A and B are chiral molecules. So a chiral center, again, is a center that is surrounded by 4 different groups. A chiral molecule is a molecule that has a chiral center and it has a mirror image. Let's consider the following molecules in there. So how many chiral centers you have? You need to go over every single sp3 hybrid carbon. So these carbons in here, these are sp2. You skip them. So let's go ahead and consider every single carbon. So this carbon over here is an sp3 hybridization. It has 4 different groups around it, and don't forget the hydrogen. We're showing the skeletal form, so there is a hydrogen in there. So this is a group. The CH3 is another group. This whole thing is another group, and this whole thing is another group. You can see these are 4 different groups in there. Going to this carbon here, this carbon has 2 groups that are the same. Do you see them? So it is not a chiral center. Normally we represent the chiral centers by an asterisk. So you simply put an asterisk next to the chiral center. So far I have 1 chiral center. All of these that I have them in green, these are not chiral centers in there because they don't have 4 different groups around them. Now coming to this carbon over here, this is an sp2 hybrid carbon. It's the same thing as this carbon. Those, they are not chiral centers because they are not sp3 hybridization. This one over here again is not a chiral center because it has 2 groups that are the same. This carbon here is a chiral center because it has 4 different groups around it. The groups are, let's go ahead and circle them, the hydrogen, the NO2, this whole thing, and this whole thing. And all of those are different, 4 different groups in there. Passing by this carbon has 2 hydrogens that are the same, so it is not a chiral center. This carbon over here, on the other hand, yes, it is a chiral center. So all chiral centers, we represent them by an asterisk. It is a chiral center. Again, please don't forget the hydrogen. So this is one group. This whole thing is a group. This whole thing is a group, and this whole thing is a group around the chiral center over here. So these are 4 different groups. So it is a chiral center. This is not a chiral center, but this one is a chiral center. So this here is a chiral center, and this one is a chiral center as well. And the rest of these 2 carbons are not chiral centers because they have 2 groups that are the same, which are the hydrogens. So here I have 2 hydrogens that are the same, and here I have 2 hydrogens that are the same. And here I have 2 hydrogens that are the same. So here, how many total chiral centers that I have? 1, 2, 3, 4, and 5. So I have 5 chiral centers. Okay, let's have another example in there. So if you are given a methyl cyclopentane, now within the methyl cyclopentane over here, you can simply draw a plane of symmetry that passes through the carbon and the methyl. And that is going to divide the structure into two equal halves in there. So this part is going to be the same as this part. If you have this case, then definitely you don't have a chiral molecule. Your molecule is going to be an achiral molecule. And anyways, that center that you see here is an achiral center because it is not, or it does not have four different groups around it. Let's consider the groups around it. It has the CH3, the hydrogen, and then those two groups over here that are the same. It's CH2, CH2 on both sides. So these two are the same. So this is going to make this carbon not having four different groups. It has three different groups. So it is not going to be chiral. So we call it an E-chiral center in there. On the other hand, if we place a double bond in here, then these two carbons now are going to be different than these two carbons in here. This is going to be a chiral center. Don't forget the hydrogen in there. So we have a group 2. This is an sp3 hybridization. And these two are 3, and these two are going to be 4. So here we have 4 different groups. So that is going to make this carbon an sp3 hybrid carbon. So if it is an sp3 hybrid carbon, then it's going to exist, or if it is a chiral center, then it's going to exist as a pair of enantiomer. Just go ahead and draw its enantiomer in there. So you draw the molecule and you draw its mirror image. It's a simple reflection in there. And these two are two different molecules. Stereocenter is another term that we need to define. So stereocenter is a center where it undergoes rotation. By definition, if you have a chiral center, that chiral center can undergo rotation. So we consider it to be a stereocenter at the same time. So all chiral centers are stereocenters. Take a look at this chiral center over here. The OH is in front. I can also draw the molecule. This is another molecule in here where I can have the OH to be behind. Both have one chiral center, but that chiral center undergoes rotation, and we call it now a stereocenter in addition to a chiral center. On the other hand, not all stereocenters are chiral centers. See the cis and the trans across the double bond, these are considered to be stereocenters, both of them, because the orientation of the molecules around them is different. So here, the orientation of the groups around the double bond are on the same side. Here, the orientation of the groups are on opposite sides. So cis and trans are considered to be stereocenters, but there is no chiral center involved in here. So not all stereocenters are chiral centers. Another term to define is the optical activity. A compound is supposed to be an optically active if it is chiral, meaning if it has a mirror image. So every compound that has a mirror image is considered to be a chiral compound, and that chiral compound is optically active. Now, the optical activity is measured by an instrument which is called a polarimeter. And the polarimeter is made up of a light source that shines the light in different directions. So this is the light that it shines. And the light passes by a polarizer. It's a piece that ejects the light as a perpendicular plane. So we call that a plane of polarized light. So the ordinary light is scattered in all directions. The moment it enters the polarizer, it becomes polarized and it exits the polarizer and it is perpendicular to the plane. So we call this the plane of polarized light. Now, that plane of polarized light passes by a sample tube. So, this is where your sample is in. If your compound is a chiral compound, meaning that it has a mirror image, then that plane of polarized light will be rotated by an angle alpha that you are able to view. So, by definition, a chiral molecule, these are molecules that are able to rotate the plane of polarized light by an angle alpha. Alpha is the observed rotation that you can read. And in this case, we say that chiral molecules, they are optically active. So the term optically active, we cannot measure it unless you go into the lab and perform the experiment of your molecule using the polarimeter to see if your molecule is chiral or not. But by definition, if your molecule has a mirror image, then definitely it will be capable of rotating the plane of polarized light and it will be optically active. So to have an optically active molecule, here you go, you would need to have a molecule to have a mirror image. And of course, definitely to have a mirror image, you need to have a chiral center. So we would say the molecule is optically active. The polarimeter measures the specific rotation. To measure the specific rotation, you would need the value of the alpha, which is the rotation of the plane of polarized light, which is called the observed rotation that you read from the instrument. Then you would have the length of the sample tube. The units are in decimeter, and you would have the concentration of your sample in the tube. You can put liquid samples in there, and you can put solid samples as well. And with those, you're gonna go ahead and calculate the specific rotation in there. Specific rotation is alpha in brackets. And normally within the brackets in there, we indicate the type of the light source. Here it's a deuterium and the temperature at which you calculated or you measured the observed rotation. So whatever you have here is the angle. This is the angle, the specific rotation of the plane of polarized light. Normally next to the angle, we indicate a sign. It's either positive or negative. Positive sign is when the plane of polarized light is rotated to the right, and negative sign is when the plane of polarized light is rotated to the left. There is no way that you can know the sign of the angle unless you go ahead and you read the observed rotation and you calculate the specific rotation. On the other hand, achiral molecules, these are incapable of rotating the plane of polarized light. So this is the plane of polarized light. This is the sample where it has an achiral compound. Notice that the plane of polarized light enters through the sample of the achiral molecule and exits without any deviation in its observed rotation. So alpha observed is going to be 0 in this case. So this is how I know that my molecule is an achiral molecule, so it is optically inactive. So by definition, optically inactive molecules, these are achiral molecules that are not capable of rotating the plane of polarized light by an angle alpha.